Hi everyone, I'm Narek Harutyunyan, a recent brand graduate and incoming PhD student at UC Berkeley. Today I will present our work on cross-embodiment mobile manipulation. Universal Manipulation Interface, or UMI, makes demonstration collection portable by using handheld gripper instead of teleoperating the final robot. The video shows our simulation equivalent. We teleoperate the floating end effector to collect demonstrations, simulating real-world UMI data collection. The problem appears during policy transfer. A policy trained only on the floating end effector data succeeds on the reference, but fails on the wheeled and quadruped manipulators, even though the task is unchanged. This leads to our main question. Can one shared high-level policy perform local manipulation across platforms with different kinematics, dynamics, and low-level controllers? We studied wheel Richback-Franca using inverse kinematics, a go-to with ARX5 manipulator, using a learned PPO controller, and a custom aerial manipulator using model-based controller. All received the same high-level end effector command. We built 6 ISIG lab tasks covering contact, insertion, pushing, pick and place, and articulated objects. Using scripted and teleoperated demonstration, we trained a diffusion policy with wrist RGB camera and effector proprioception, a clip encoder, and a unit denoiser. Preliminary across 120 evaluations we performed, the floating reference reached 95% success. Without adaptation, this drops to 58% on good to ARX5 and 55% on Richback-Franca. A shared action format alone is not enough. We proposed 3 different directions: retarget data before training, adopt the shared policy after training, or learn the shared task latent with an embodiment-specific decoder. So far, only the first approach has been tested. Those videos shows approach 1. We first teleoperate the floating end effector, or AVI or UMI equivalent. We then replay the exact commands through the mobile manipulators and re-record their observations. Successful replays here shows that the robots can actually perform the task quite well. The original policy fails because it doesn't account for controller drift, tracking error, and platform instability. We trained a new diffusion policy using this replayed embodiment-specific data. Preliminary evaluations improve, but remain inconsistent. Here you can see only the evaluations that actually work on those platforms. Data refinement and pre-training adaptation therefore help, but not sufficient alone. Motivating approaches 2 and 3. For hardware testing, we collected peg and hold demonstrations with our UV-style gripper and trained the separate real data policy for linear robot. We also preparing for aero and remaining mobile platforms for evaluation. Those tasks are still work in progress. For the next steps, we will scale task diversity, recreate the task in real world, and finish all the hardware platforms, and combine replay-based pre-training with post-training adaptation for more reliable transfer. I want to thank CMU's Robotics Institute Summer Scholar Program, or RIS, and all the people behind it, especially Rachel Bursin and Professor John Dolan. Special thanks to Professor Guanxi and Yutong Wang for their amazing guidance and mentorship throughout the summer. And thank you for watching this video.